All right, so let's get on electron configuration. We want to share the visualizer. And there we go. Got my periodic tables out. Everybody good? I got a periodic table in here. Good. All right. So last time we had you go through these, is that right? And write the electron configuration here, here, and here, and basically go through and get the box diagram set up as well. So check your answers on that if you've not already done so. And I think that's what we started with yesterday. Now the main focus today is to allow you to do the electron configuration with only the periodic table. And that's a little bit harder, but once you do it a few times, you get a lot faster at it. And that's what you were to do last night with this side. So if we take a look, the first thing you need to know is the number of electrons. So if we take a look, 2 plus 2 plus 3, that is 7. We want to find the element with the number of electrons of 7. We look on the periodic table, we look at the atomic number. That is 7, that is nitrogen. 2 plus 2 plus 6 is 10, plus 2 plus 6 is 18. We find on the periodic table 18, that is argon. Now it says give the complete electron configuration for each of the following. So let's go ahead and let's start with an easy one first. I'm just going to do these in order of easy to complex. We'll start with lithium. Lithium has 3 electrons total. I'm just going to put that there. So 1s2. So here's 1s2, 2s. Remember these first 2 columns are s's. 2s1. Let's do calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, these give us our s's and our p's. So calcium has 20 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 10, 20. Calcium, we said, has 20 electrons. We add up these superscripts and we get 20. Let us do sulfur. Sulfur has 16 electrons. So basically, we want to have something similar to this, but only with 16. That means we're going to lose 2 from here and 2 from here, right? So 1s2, 2s2, 2p6, 3s2, 3p4. Oh, I went too far. 3p4. There we go. 10 plus 6 is 16. Bromine? Bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, the D's are always one behind. So 4s2 drops down to 3d10. Bromine drops back up to 4, or goes back up to 4p5. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And again, that is 35. We can count that. 2 plus 2 plus 6 is 10, plus 2 plus 6 plus 2 is 20, plus 10 is 30, plus 5, 35. Now, krypton has 36. So it's going to be the same as bromine, but instead of 4p5, we're going to have 4p6. Or we could just follow along the periodic table again, and we would see that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Krypton. Yeah. All right. So what we've been making so far are what we call ground state electron configurations. And we can actually excite electrons, and you do this all the time. For example, I can add electricity, and I can excite the electrons in this bulb. Whenever I excite those electrons with electricity, they jump up to higher energy levels. And when they drop back down, they emit that energy in the form of electromagnetic radiation. In this case, the electromagnetic radiation is light. Right? So electron configurations that we studied are called ground state electron configurations. Occasionally, electrons will absorb additional energy. If we heat them up, use radiation, like put them in a microwave or something like that, or even electricity. When we do that, these electrons jump up to higher energy levels. So let's say that you have hydrogen. We have one electron here. If we give that electron energy, boom, it may jump up from that first ring to a later ring. Remember, we said the further away from the nucleus you get, the more energy you have. So we just gave that electron a lot more energy. Boom, it jumped away from the nucleus. When it releases that energy back out, it releases it in what we call a photon. A photon is a packet of energy. When it releases that photon back out, it drops back down to its ground state level. So we do something to the electron to excite it. It goes further away from the nucleus. It then emits that photon of energy, and then it goes towards the nucleus. I'm sorry? Yeah, so it gains energy. It goes away from the nucleus because it has more energy. It can be further away. Then it gives off that energy, and it goes back to its original ground state. So such an atom is called an excited atom, and its electron configuration is called the excited state. So we want to be able to tell whether or not an electron is in its excited state. So the best way to do that is to inspect the electron configuration and determine if it follows the alpha sequence. An atom can have just one ground state, but many, many different excited states. So let's take a look here. 1s2, 2s2, 2p6, 3p1. Now that's not exactly what we would normally get when we do the electron configuration of something. After 2p6, what comes? What level comes? Not 3p1, but what? Here's 2p6. Then what's next? 3 what? Louder? That's it. If this is 2p6, what comes after 2p6 normally?
Is it 3s?
Yeah, very good. 3s. So an electron that normally would be in 3s has jumped up to 3p. So this is excited. The number of electrons we still find the same way, 2 plus 2 plus 6 plus 1. That's 11. But the 3s, 1 electron has been excited and it has gone up to another energy sublevel. 1s2, 2s1, 2p4. So normally we would expect at ground state 1s2 to be followed by 2s2. But whatever electron was in that 2s2 part has gained energy and has jumped up to the 2p. So again, this is excited. 2 plus 6 plus 1 is 7. 1s2, 2s2, 2p6, 3s2, 3p6. 10 plus 8 is 18. And that is exactly as we expected it to be. That's exactly the normal way that we expected it to be. 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. After 3p6, before we get to 3d, we actually get 4s in there. So that means 2 electrons in this have jumped and they are in the excited state. 2 plus 2 plus 6 is 10 plus 6 plus 7 is 13. It's 23, 25. So just keep that in mind. There should be right here the 4s, which isn't there. If somebody showed you an electron configuration that was impossible, how could you tell? Well, first you need to understand that in addition to the ground state and excited states exist, and these are possible. For an electron configuration to not be possible, you must have 2 things. The electron configuration shows a sublevel that does not exist, or a sublevel has exceeded the capacity. For example, S can only hold 2, P can only hold 6, E can only hold 10. So if we take a look here, and give me whether or not this is possible or impossible. 1s2, 2s3, 2p4. Is it possible or not? What do you think? 1s2, 2s3, 2p4. What does this look different? Is there anything about this that looks different than anything we've ever done before? Louder? The 2p4? What's wrong with that? Let's take a look. 2p, 1, 2, 3, 4. That's going to be okay. So 1s2, 2s3. Is there anything wrong with either of those, or is this possible? Nope, it's not possible. There's something definitely wrong with it. Yeah, 2s should not be able to hold 3. 2s can only hold 2, right? By definition, s can only hold 2. So that's impossible. I'm going to put an I there. 2s2, 2p6, 3s2, 3p1. Is this possible? What are we normally used to seeing? We're used to seeing always 1s first. But that doesn't matter because that 2s can have 2, 2p can have 6, 3s can have 2, and 3p can have 1. This is possible. It's just that there's multiple electrons that are excited. So that's excited state electrons. How about here? 1s2, 2s2, 2p6, 2d10, 3s1. What's wrong with this? Let's get some people from home if they can. What's wrong with this thing? Problems with this guy. 1s2, 2s2, 2p6, 2d10, 3s1. Louder? 2d10 is correct. The home guys did not want to play, so we had to do it here. This 2d10 is incorrect. The second principal energy level only has two. It has a 2s and a 2p. There is no 2d. Last one, 1s2, 2s2, 2p6. This is perfect like we normally would be used to seeing it. That is the ground state for sure. Last thing today, alternate ways to represent an electron configuration. Some people like to keep all the numbers together. That way, when we look at this, we know that it has 5 valence electrons. Sometimes they keep them all together and they only put the number in front of the whole section. I actually don't like this way, but if you go online, you may see this. So if we were to do this, we would have 1s2, 2s2, p6, 3s2, p6, d7, 4s2. So that way somebody can see what the highest energy level is and see what how many electrons it has. The reason I don't like this is that makes some people just look at the 4s2 and go, oh, they're talking about calcium. It is not calcium. 2 plus 2 plus 6 is 10, plus 2 plus 6 plus 2 is 20, plus 7 is 27. So it's not calcium, it's actually cobalt, right? But by writing it in this fashion, a lazy person might just look at 4s2 and go, oh, it's calcium. So notice what I did again. I took all of the 2s and put them together. I put all the 3s together and the 4. You won't see me write it like this except for this exercise. I only do this so that you understand that those do exist out there. The last thing we want to do today is that noble gas or abbreviated configuration. So if we take a look here, the noble gas or the abbreviated configuration. For electron configurations of atoms with a large number of electrons, the configuration is also presented in abbreviated form. This is done by selecting the noble gas that goes right before the element and adding on the next sublevels in the alpha sequence. So here's barium. That's a big old thing. But here is the electron configuration of neon. So if we go right there, we've got the electron configuration of, I'm sorry, not neon, xenon. We got the electron configuration of xenon. So why not just box that in? We can box in xenon because it's right before barium, and then we can use the rest of it, 6s2. The reason we can do this is all of these have filled energy levels, complete filled energy levels. So the noble gases are the only ones that you can put in brackets and do this with. So let's take, for example, calcium. Let's say I'm feeling really lazy and I don't want to write out the full thing for calcium. I go 1, 2 back, and I see argon. So I can go calcium, and I can go, its electron configuration starts with all of argon's electron configuration, and then also 4s2. That's the abbreviated form. What if I wanted to do manganese? Well, again, the noble gas that precedes manganese is argon. So I'm going to do all of argon's electron configuration, then 4s2, and then 3d1, 2, 3, 4, 5, 3d5. Pretty easy to make it. The other way is to look at how we look at the noble gas configuration and figure out what element they're talking about. For this, well, you add the superscripts. 2 plus 8 is 10, plus however many electrons argon has. So argon has 18. 18 plus 10 is 28. So that is nickel. Krypton plus 16. 2 plus 4 plus 10 is 16. Plus krypton, 16 plus 36, that's 46, 52. 52 is tellurium. That's what you've got for, go ahead and finish that up for the rest of this period. That's your homework. And then we'll take a look at this review right before Wednesday, not next Wednesday, but the following Wednesday's quiz. And then we'll start this math. We're about halfway through the unit at this point. If you have questions or whatnot, by all means, stick around and ask. But whatever this page is, this page, do that for your homework. Have a great day. If you have questions, by all means, stick around. Otherwise, bye. Whew. Whew. Are you watching me on that too? Somebody asked you or whatnot. I can stand up there. What is it? After I was 2 months. Phillips and landfill, that won't be another 50 years. different colors on the side. Over there. Strawberry over here. Basically, what we're doing is we're exciting the electrons, setting up a higher level. But when they come back, they emit a photon. Those photons are for certain wavelengths of electromagnetic radiation that we perceive as color. Right? So we have this visible spectrum. You know, this is like seven phase. What's there, right? Red, orange, yellow, green, blue, and violet. What we're thinking is it's putting out these certain wavelengths that make those colors for us to see. Kind of cool. We're going to study that. Yeah, so yeah, visible light is the light you can see, and non-visible light is ultraviolet, which we can't see, and below is the light for red, which we can see. Yeah. Yeah, if you have a camera, you have to think like that. Our eyes cannot. So that's what I meant when I said exciting electrons. We also see it with electricity as well. And basically, that's the way light works. We get an electricity, they emit photons of light. That's how we light up the room. Right? See the stars, salt, this is careful to do. I'm kicking you off your car so I can get the video for this, all right?